Good afternoon. Today we're going to be talking about section 5.2, definite integrals. So the topic is net areas, and the question is, how do we interpret Riemann sums when f is negative at some or all points of our interval a to b? And we're going to start with an example as we normally do. So evaluate and interpret a midpoint Riemann sum with the interval a to b equals 1 to 3 and n equals 4 for the function f of x equals 1 minus x squared. So the first thing we do is we determine delta x. Delta x equals b minus a over n. So it's 3 minus 1 over 4 equals 0.5. So our intervals become 0 to 0.5. Sorry. Our intervals are 1 to 1.5, 1.5 to 2, 2 to 2.5, and 2.5 to 3. And we're doing a midpoint Riemann sum, so our midpoints of these subintervals are going to be 1.25, 1.75, 2.25, and 2.75. And now all we have to do is plug those in to our summation. Our summation is f of xk star times delta x, which is the same from k equals 1 to n, which is the same k equals 1 to 4, f xk star, and our delta x is 0.5. This works out to be f of 1.25 times 0.5 plus f of 1.75 times 0.5 plus f of 2.25 times 0.5 plus f of 2.75 times 0.5. And when you plug this into your calculator, you get negative 0.5625 minus 2.0625 minus 4.0625 minus 6.5625 all times 0.5. And all of that works out to be negative 6.625. So the answer to our Riemann sum is negative, but think about what an area is. Area is always a non-negative quantity. That is, it's always positive or 0. So the Riemann sum doesn't approximate the area of the region between the curve and the x-axis, but the values of fk star are negative of the heights of the corresponding rectangles. Therefore, the Riemann sum approximates the negative of the area of the region bounded by the curve. So what we're saying is, this region still has positive area, but because it's below the curve, we say that it's negative. So the negative sign just indicates whether our function is positive or negative, if the area lies above the x-axis or below the x-axis. So let's try this one. Evaluate and interpret the left Riemann sum with a to b equals 0 to 3 and n equals 6 for f of x equals 1 minus x squared. And again, to save the work, delta x equals 0.5. So our grid points are 0, 0.5, because we're doing a left Riemann sum, 1, 1.5, 2, 2.5, and 3. Sorry. Not 3. 3 isn't there. So we've got 1, 2, 3, 4, 5, 6 points that we're looking to. And these are all of our xk stars. And now we just plug this into our Riemann sum. So we have f of 0 plus f of 0.5 plus f of 1 plus f of 1.5 plus f of 2 plus f of 2.5, all times 0.5. And these are our positive contribution, while these are our negative contribution. So we get 1 plus 0.75 plus 0 minus 1.25 minus 3 minus 5.25, all times 0.5. And that works out to be negative 3.875. So that's the value, but what does the graph look like? And the graph looks something like this. So we've got a little bit above the x-axis and we've got a little bit below the x-axis. So what does this mean? This means that we're finding the net area. Consider the region R bounded by the graph of a continuous function f and the x-axis between x equals a and x equals b. The net area of R is the sum of all of the parts of R that lie above the x-axis minus the sum of the areas of the parts of R that lie below the x-axis. So this answer negative 3.875 means there's more that lies below the x-axis than there is that lies above the x-axis. But it's still the value of all of the positive parts minus all of the negative parts. So Riemann sums for f on a to b give approximations to the net area of a region bounded by the graph of f and the x-axis between x equals a and x equals b, with a less than b. But how can we make these approximations exact? How do we know that we're getting the real answer instead of a number that's just kind of close to the answer? If f is continuous on a to b, it's reasonable to expect the Riemann sum approximations to approach the exact value of a net area as the number of subintervals n goes to infinity, and as the length of the subintervals delta x goes to 0. In terms of limits, we write the following. Net area equals the limit as n goes to infinity of the summation of f of xk star times delta x. And here's what this looks like graphically. So here we have 1, 2, 3, 4, 5, 6 intervals, and we can see that this isn't a very good fit. But even if we go to n equals 40 intervals, we have a much better fit. And n equals 75 intervals, we again have a much better fit. So what if we have infinitely many intervals and they're of infinitely small width? Then we're going to get the actual net area. And that's going to be a really big concept for moving forward. The Riemann sums we've used so far involved regular partitions in which the subintervals all have the same length, delta x. Now just briefly consider a general partition in which delta x are not necessarily the same length. One might be smaller than another, one might be larger, two might be totally different sizes. Further, consider letting xk star be anywhere within the subinterval and not necessarily at the right, left endpoint or midpoint. When we do this, we create a general Riemann sum. And a function f defined on a to b is integrable on a to b if the limit as delta goes to 0 of the the summation of f of xk star times delta xk, where delta xk is a particular subinterval width, exists, and is unique over all partitions of a to b and all choices of xk star on a partition. This limit is the definite integral of f from a to b, and we write the following. So let's examine this a little bit further. And I really want to relate a few things. Here we have the upper limit and here we have the lower limit. Whereas here we have the upper limit of integration, and here we have the lower limit of integration. We still have f of x and f of xk star, and we still have something that looks like delta x becomes dx. When we take that limit to let, oh my gosh, when we take the limit of the width of our intervals to go to 0, and we have infinitely many of them, then that turns delta x into dx. So here's another theorem that you might have to use. If f is continuous on a to b, or bounded on a to b with a finite number of discontinuities, then f is integrable on a to b. Let's do a quick example. Given the graph of the function, find the values of the following definite integrals. Our first one is the integral from a to b of f of x. Now this black line here is f of x, and we're interested in a to b. So we're interested in the area bounded by the curve in the x-axis right here. And in fact, it simply tells us that that area is 12. Now we're interested in b to c. And we have to remember that this area lies below the x-axis, so our sign should be negative. Negative 10. Now we're looking from C to A. And it's going to be negative 10 from C to A. I'm sorry, this should be A to C. Wait, that's what I have written. I'm sorry. From A to C, so we're interested in this interval, so it's going to be 12 minus 10. The net area is 2. And then we're looking for the interval from B to D. So it's going to be this area minus this area. So we have 8 minus 2, or 8 minus 10 equals negative 2. So that's how we find it using a graph. So here are some properties of definite integrals. If I integrate from a to b of f of x dx, then the integral of b to a is going to be the negative value of that. If my limits of integration are identical, that is, if I'm integrating from a to a, then my value equals 0 because we're taking no width. Imagine trying height times 0 width equals 0. You can imagine it that way. The integral of a sum is the sum of the integrals. So if I have two functions, f of x plus g of x, integrated from a to b, then I can split them up and have integral of f of x from a to b plus the integral of g of x from a to b. Next, we of course have a constant multiple rule. If I've got a function c times f of x integrated from a to b, I can pull out my c and just do c times the integral of a to b of f of x dx. Next, we can always split integrals up. So maybe it's easier to integrate from a to a point p and then from p to b and add these two areas up than it is to do this. And that's totally equal. That's totally fine. So the integral from a to b of f of x dx is the same as the integral from a to a point p of f of x dx plus the integral of point p to b of f of x dx. As long as p lies between a and b, we can always do that. And in fact, we can always do the opposite. If I know the integral of this bad guy, but I just want this, then I can say this minus this equals this, and any combination thereof. And finally, integrals of absolute values. How do we interpret this? And the answer is we flip everything to be above the x-axis. So that region becomes this region. And it's not just as simple as saying absolute value of all of these things. You might have to separate your integral into three pieces, right? So you might have to go integrate from here to here and make that value positive, and then integrate from here to here. So this one can be tricky. Now, I'm going to state these and not give proofs of them, and because I don't think that the proofs are very useful or intuitive, that matter, from the textbook. So I'm just going to state these without proof. And if you want to see the videos on why these work, then watch Bryce's videos because I'm sure he goes into it. But pretty much, if a function is greater than 0 from a to b, then the integral of that function is going to be greater than 0. So that is to say, I have a function here, and it always lies above the x-axis. That means that when I integrate, when I find the area under the curve, it's always going to be positive. It's never going to be negative. Now, if I've got a function f of x that's always greater than g of x on an integral a to b, then the integral from a to b of f of x dx is always going to be greater than or equal to the integral from a to b of g of x dx. Sorry. Sometimes we get sloppy. And that's to say that the area under this curve, f of x, is all of this, while the area under the curve of g of x is just this. So the area under the curve of f of x is all of g of x plus a little bit more. So that's pretty much what that one's saying. Next, I'm saying that we can bound these values. So let lowercase m be a value that's less than or equal to f of x at some point, and let uppercase m be a value that's greater than or equal to f of x at some point. And here, I've chosen my capital M to be this value, so I'm going over like that, and my lowercase m to be this value, so I'm going over like that. Then, my lowercase value m times the width a minus b, or b minus a, so this whole area is going to be less than the integral of my function, which is this whole area. But if I take this top bound, this upper bound, and I find the area between that, and I multiply this value, m, times b minus a, then I get this whole region, which is greater than my value. So we can always bound our integrals. Finally, let's do one example, evaluating definite integrals using limits. So find the value of the integral from 0 to 2 of x cubed plus 1 dx by evaluating a right Riemann sum and letting n go to infinity. And here's how we're going to do that. First, my interval is a to b equals 0 to 2, and we want to divide it into n many subintervals. So delta x equals b minus a over n equals 2 over n. That means all of our grid points, which we learned about last lecture, are going to be a plus k times delta x, because we're doing a right Riemann sum, which equals 0 plus k times 2 over n. So we just have 2k all over n. When we let f of x equal x cubed plus 1, the right Riemann sum becomes k equals 1 to n. We replace x with 2kn, 2k over n, cubed plus 1, times our delta x, which is 2 over n. Well, I can pull out my 2 over n and leave the sum alone. I'm going to go ahead and cube that, so I get 8 k cubed over n cubed plus 1. I can separate these into two sums and pull some more stuff out. So I get 2n times 8n cubed times my sum, k cubed, plus 2 over n times the summation of the value 1, from k equals 1 to that. Now I simply use those rules that I've had beforehand on what the value of, here, let me copy this and bring it to another slide. This bit we already know. So let's say 2n times 8n cubed times this value, which is n squared, times n plus 1 squared, all over 4, plus 2 over n times, this one is just c times n. Our c is 1, so it just equals n. Altogether, this is 4n squared plus 2n plus 1 over n squared plus the value 2. So now, I'm making a mess. Our integral from 0 to 2 of x cubed plus 1 dx equals the limit as n goes to infinity of my summation f of xk star times delta x n k equals 1. This equals the limit as n goes to infinity of our representation of our summation, which is 4n squared plus 2n plus 1 over n squared plus 2. Here we can pull this 4 out in front, so I get 4 times the limit, n goes to infinity, of n squared plus 2n plus 1 over n squared plus the limit, n goes to infinity, of 2. Well, this whole term is just n squared over n squared, so it's equal to 1. So I've got 4 times 1 plus 2 equals 6. So the area under the curve is 6. And when we did this example earlier, we conjectured that it was probably in between 5 point something and 7 point something, and sure enough, it is. That's it for me today.